I want you to stop for just 1 second. Not to worry, not to panic, just to tune into something your body has probably been signaling for a while now, something you have most likely been quietly brushing aside. When you look at a lamp or a lit screen in the room you are sitting in right now, does the light feel a little harsher than it used to? Not dramatically so, just a little more than you remember. When you try to read something small at night, does the text take a beat longer to come into focus than it did 10 years ago? When you are driving after dark, do oncoming headlights feel like they spread outward and bloom in a way that makes you squint or briefly look away? And when you step from a brightly lit room into a darkened hallway, does it take your eyes noticeably longer than before to adjust and find their footing? None of these things are dramatic enough to send you to an emergency room. None of them probably felt urgent enough to book an appointment over. They are quiet, gradual, the kind of thing you mention once in passing, and then file away under just getting older, accepting it as the price of the decades behind you. But here is what I need you to understand before we go any further. And I want you to hear this clearly because it matters. What you are describing is not random. It is not simply the unavoidable cost of aging. And most importantly, it is not something you are powerless over. The quiet changes in your night vision, the glare, the slower adjustment, the blurry contrast in dim environments. These are downstream signals of a specific and well-understood biological process. And that process has a nutritional dimension that almost nobody is talking about in a way that is practical and actionable. I am Dr. Megan Foster. I have spent over 2 decades working with patients navigating age-related health changes. And vision decline is one of the areas where I see the most unnecessary suffering. Not because nothing can be done, but because most people are never given the full picture. They are handed a stronger prescription and sent home. They are told their eyes are just aging, and they accept that because it sounds authoritative and final. But it is incomplete. Incomplete information leads to inaction. And inaction allows a process to continue that with some understanding and some consistent effort does not have to progress the way it typically does. So today, I'm going to give you the fuller picture and I'm going to keep it practical because information without a clear path forward is not actually useful. By the end of this video, you are going to understand something that most people never learn. What is actually happening inside the eye after 60? What occurs in the retina specifically while you sleep? And 7 fruits that research suggests can directly support the protection and overnight repair of the most critical visual tissue in the human body. And before we dive in, drop a comment right now. Have you noticed changes in your night vision over the past 5 to 10 years? Describe what it actually feels like for you. Is it glare, slower adjustment, reduced contrast, blurrier edges when the light is low? The reason I ask is not just conversational. When people start naming what they are experiencing, they realize how many others share it. And that shift from personal failure to shared biological pattern is genuinely important for motivation. Comment now, I read them. Now, let me take time to properly explain what is happening inside the aging eye because the biology here is genuinely interesting. And once you understand the mechanism, everything I am going to tell you about these 7 fruits will make complete logical sense rather than feeling like a list of health claims you just have to take on faith. Most conversations about aging vision begin and end with the lens. The lens sits just behind the pupil and its job is to focus incoming light onto the back of the eye. As we age, the lens gradually loses flexibility. The proteins inside it change structure over time. It becomes stiffer and less able to shift focus quickly between near and far distances. This is why the majority of people need reading glasses by their mid-40s. That part of the story is real and well understood. But the lens is not the whole story, not even close. The part of the story that almost no one talks about in practical terms is what is happening further back in the eye, in the retina, and more specifically in how the retina ages, what it needs to function well, and what happens to it during the hours you are asleep. Your retina is a thin layer of living tissue that lines the inside back wall of the eye. Scientists who study it consistently describe it as the most metabolically demanding tissue in the entire human body, pound for pound. What that means in plain terms is that relative to its size, the retina burns through the more oxygen and more nutrients than any other tissue. It runs hot metabolically speaking because it is doing an enormous amount of work continuously. Inside the retina are specialized cells called photoreceptors. These are the cells that actually detect light and convert it into electrical signals that travel along the optic nerve to the brain where they become the images you see. There are 2 types of photoreceptors. The first type is called cones. Cones are concentrated in the center of the retina and they handle bright light vision. They are responsible for color perception, fine detail, and sharp central vision. Reading, recognizing faces, seeing fine print, appreciating color differences, all of that is con function. The second type is called rods. Rods are distributed across the outer regions of the retina and they specialize in low light and dim light detection. rods are dramatically sensitive to light cones. A single rod cell can respond to a single photon of light under the right conditions. They are responsible for your peripheral vision, your ability to detect motion in dim environments, and your ability to see when the lights are low. Night driving, navigating a darkened room, reading in candlelight, adjusting after coming in from outside, all of that depends on rod function. And here's where things get interesting in the context of aging. Rods depend on a molecule called rhodopsin to do their job. Rhodopsin is a light-sensitive pigment that sits inside the rod cells and it works through a cycle. When light hits rhodopsin, the molecule changes shape and triggers the electrical signal that the brain reads as vision. But in doing so, the rhodopsin is consumed. It breaks down. For the rod to keep working, rhodopsin has to be continuously regenerated. That regeneration requires vitamin A as a direct chemical input. No vitamin A, no rhodopsin regeneration. No rhodopsin, no dim light vision. This cycle, the depletion and regeneration of rhodopsin, is happening in your eyes constantly. Every moment your eyes are open and receiving light, rhodopsin is being used up and rebuilt. When vitamin A is present in adequate supply, the regeneration keeps pace with the depletion and your night vision stays functional. When vitamin A is insufficient, the regeneration falls behind. Rhodopsin levels drop and the rods begin to struggle in low light conditions. The earliest symptom is always difficulty seeing in dim light and slower adjustment when transitioning from bright to dark environments. That is not a coincidence. That is exactly the mechanism playing out in real time. Now, the rods are one part of this story. The other, and perhaps even more important part for long-term visual health, involves the center of the retina, a small region called the macula. The macula is roughly the size of a pencil eraser, but it contains the highest concentration of cones in the entire eye, and it is responsible for everything you think of as sharp, detailed central vision. Reading, driving, recognizing a face, watching television, using a phone or computer, all of that is macula. When the macula is healthy and well protected, central vision is sharp and reliable. When the macula deteriorates, central vision blurs and eventually erodes in ways that significantly affect independence and quality of life. The macula is under an extraordinary and constant amount of stress. Every hour that light enters the eye, a byproduct called oxidative stress is generated inside the retina as a natural consequence of visual processing. Think of oxidative stress as a form of biological friction. Small, highly reactive molecules called free radicals form during the normal activity of the photoreceptor cells, and if they are not neutralized quickly, they damage nearby tissue. The macula, because it handles the most intense and most detailed visual processing of any region in the eye, produces more of this oxidative byproduct than any other part of the retina. The body has a natural defense against this. It is called the macular pigment. This is a physical protective layer made of two specific compounds, lutein and zeaxanthin, that deposits directly inside the macula and acts as a biological filter. The macular pigment does two critically important things. First, it absorbs high-energy short-wavelength light before that light can penetrate to the photoreceptor cells beneath it. Think of it as a built-in internal pair of sunglasses specifically for the most vulnerable part of your eye. Second, it directly neutralizes free radicals as they form, preventing oxidative damage before it accumulates. The macular pigment is, in the most literal biological sense, the macula's own protection system. Here's the critical piece. The body cannot manufacture lutein or zeaxanthin on its own. Unlike many protective compounds, these two cannot be synthesized internally. They can only be obtained from the diet, and the body, recognizing their importance, selectively transports them from the bloodstream and concentrates them specifically in the macula. This selectivity is remarkable. Of all the carotenoids in the diet, only these two are targeted and deposited into this specific location. The body essentially treats them as structural components of the eye, not just general antioxidants. Now, by the time most people reach their 60s, macular pigment levels have often been declining for years, sometimes for decades, because the modern diet is genuinely and significantly low in lutein and zeaxanthin. These compounds were historically present in the diet through organ meats, egg yolks from pasture-raised hens, and large amounts of dark leafy greens. For the majority of people today, those sources have largely disappeared from regular eating, and without consistent replenishment through the diet, the macular pigment layer thins over time. The biological filter weakens, the protection erodes, and the oxidative damage that would previously have been absorbed and neutralized now reaches the photoreceptor cells directly. This is not a theoretical concern. Large longitudinal population studies have followed tens of thousands of people over 10 to 20 years and consistently found that individuals with lower macular pigment density show significantly higher rates of age-related macular degeneration. Not because their genetics are dramatically different, but because their protective layer has been depleted over time by insufficient dietary intake of the compounds the body needs to maintain it. Now, Let me talk about the nighttime dimension of this specifically because this is the piece that is almost never discussed in accessible terms, and it is central to why the timing of what you eat matters for eye health. During the day, your eyes are actively processing. Every system supporting the retina is running at or near full capacity. The photoreceptors are firing continuously. The support cells around them are working hard to keep up with demand. Blood flow to the retina is at its daytime levels. Metabolic activity is high. At night, when you sleep, the pattern changes in important ways. The photoreceptors are no longer receiving light stimulus. The metabolic demand of the retina drops significantly. And critically, the body activates its cellular repair and maintenance programs. The retina undergoes a meaningful portion of its structural maintenance during sleep. The retinal pigment epithelium, a layer of support cells that sits just beneath the photoreceptors and is responsible for much of their day-to-day maintenance, does some of its most important work during the overnight hours. It processes and removes metabolic waste products that accumulate during the day. It recycles components of the visual cycle. It repairs minor oxidative damage before it has a chance to compound. This overnight repair window is real and it is important, but it requires resources to run effectively. It requires adequate antioxidant compounds. It requires good circulation to deliver oxygen and nutrients to the tissue during repair. It requires the raw materials for the visual cycle to be replenished. When these resources are insufficient, the overnight maintenance does not run at full capacity. Damage that accumulated during the day carries forward. Waste products that should have been cleared are not fully removed. The visual cycle components are not fully replenished. And this partial insufficient overnight repair is what over months and years shows up as the progressive visual changes that people associate simply with getting older. What you eat in the hours before sleep is one of the inputs into that overnight repair window. Specific nutrients circulating in the bloodstream during the early stages of sleep, when repair processes are ramping up, are available to the tissues that need them. This is the mechanistic reason why evening timing of these specific foods is relevant. It is not about a dramatic transformation in a single night. It is about consistently providing the right inputs during the window when the eye is doing its most active repair work over weeks and months, until the nutritional environment in the eye has genuinely shifted. The research supporting this approach comes from multiple directions. Studies from institutions including Harvard-affiliated ophthalmology research groups have confirmed that dietary patterns rich in the protective compounds found in these fruits are associated with significantly better long-term visual outcomes. Same age groups, different dietary patterns, meaningfully different rates of visual decline over 10 to 20 years of follow-up. That pattern is robust and has been replicated across independent research groups across multiple decades. Now, I want to talk about something that does not get enough attention in discussions of eye health after 60, and that is the connection between blood vessel health and vision. The retina has no backup blood supply. Unlike most organs which receive blood from multiple arterial sources, the retina is entirely dependent on a single arterial system and a network of capillaries so fine that red blood cells must navigate them in single file. This is an extraordinarily delicate supply chain, and as the body ages, the health of this microvascular network becomes one of the most important determinants of retinal function. The inner lining of blood vessels, called the endothelium, is responsible for regulating blood flow, responding to the demands of the tissue and maintaining the structural integrity of the vessel walls. When endothelial function is good, blood flows smoothly and the retina gets what it needs. When endothelial function declines, circulation becomes sluggish, irregular, and less responsive. The retina, with its massive metabolic demand and its complete dependence on this single supply line, is one of the first places where vascular decline shows up as functional impairment. Several of the fruits on this list work specifically on this vascular dimension. And understanding that helps make sense of why foods that are primarily associated with heart health also directly protect vision. The mechanisms overlap. The same compounds that keep arteries healthy also keep the tiny vessels of the retina healthy. Cardiovascular and eye health are far more connected than most people realize. So let us get into the 7 fruits. I am going to walk through each one specifically. What it does, why it matters, the evidence behind it, how to use it practically, the right amount, the right timing, and the common mistakes that cancel out the benefit. Starting with number 7, kiwi. Kiwi is almost always framed as a vitamin C food and left there. But inside the eye, vitamin C is doing something more specific and more important than general immune support. The lens of the human eye contains one of the highest concentrations of vitamin C found anywhere in the body. It is there in that concentration deliberately because vitamin C is one of the primary defenses the lens has against the oxidative stress that over decades causes the lens proteins to clump and cloud. That clouding is a cataract. Large population studies have found that higher dietary vitamin C intake is associated with significantly lower rates of cataract progression over time. In one major twin study, participants in the highest vitamin C intake group had a 60% lower risk of cataract progression over the study period compared to those in the lowest intake group. That is a substantial difference. But vitamin C also performs an important supporting role for other antioxidants in the eye. After vitamin E neutralizes a free radical, it becomes oxidized and inactive. Vitamin C regenerates vitamin E back into its active form so it can continue working. Without adequate vitamin C, you lose not just vitamin C's own antioxidant activity, but also a large part of vitamin E's effectiveness. Two protective systems weaken for the price of one deficiency. Vitamin C is also essential for collagen production. The tiny blood vessels supplying the retina rely on collagen for structural integrity. When vitamin C is chronically low, vessel walls become more fragile and vulnerable to micro leaks and damage. That feeds directly into the vascular dimension of retinal health. One kiwi in the evening eaten as a whole fruit, paired with a small handful of nuts or a few pieces of natural cheese. The fat slows glucose absorption and helps fat-soluble antioxidants from other foods eaten around the same time absorb more completely. Never juice kiwi. Juicing removes fiber, concentrates sugar, and turns a well-structured food into a blood sugar spike. Whole fruit only. Number 6, oranges. Beyond vitamin C, whole oranges contain a class of flavonoid compounds, particularly one called hesperidin that has been studied specifically for its effects on blood vessel health in ways that are directly relevant to the retina. Hesperidin works primarily by supporting endothelial function, the health of that critical inner lining of blood vessels discussed earlier. Clinical trials using citrus flavonoid supplementation have shown measurable improvements in endothelial function markers within 4 to 8 weeks of consistent use. One placebo-controlled trial found that participants taking hesperidin showed significant improvements in blood vessel responsiveness, the ability of vessels to dilate appropriately in response to demand compared to the control group. For the retinal microvessels specifically, better endothelial function means more responsive and more efficient circulation. The photoreceptors get more oxygen. Metabolic waste is cleared more effectively. The conditions for overnight repair are better supported. This is not a general wellness claim. This is a specific mechanistic pathway connecting a specific compound in oranges to retinal circulation. One whole orange in the evening, whole fruit only, not juice. Even fresh squeezed orange juice has most of its fiber removed, which eliminates the slow absorption benefit and creates a faster blood sugar rise. And avoid pairing citrus fruit with high sugar desserts or sweetened snacks. The combined glucose load undermines the metabolic stability you are trying to maintain in the hours before sleep. Number 5, papaya. Papaya is one of the richest sources of beta-carotene available in a commonly eaten fruit, and the eye health story of beta-carotene goes considerably deeper than most people realize. Beta-carotene is what scientists call a provitamin. Your body converts it into vitamin A on demand in the amounts it needs and uses it across multiple systems in the eye. You already know that vitamin A is required for rhodopsin regeneration in the rod cells. But vitamin A also plays an essential role in maintaining the health of the conjunctival epithelium, the delicate surface tissue of the eye. This surface tissue requires vitamin A to maintain the goblet cells that produce the mucin layer of the term. When vitamin A is inadequate, goblet cell density drops. The term becomes unstable and the eye dries out. This is one of the reasons why dry, irritated eyes become more common after 60. It is not purely a structural aging story. It has a nutritional dimension that is frequently overlooked. Beyond the direct vitamin A pathway, papaya also contains a carotenoid called beta-cryptoghan. This compound has antioxidant activity inside the retina and is being studied for a potential contribution to macular protection alongside lutein and zeaxanthin. The evidence is still developing compared to those two primary carotenoids, but the biological plausibility is real. And here is something particularly valuable about getting your vitamin A pathway from beta-carotene and fruit rather than from performed vitamin A in supplements or liver. Beta-carotene from plant sources is self-regulating. The body converts exactly as much as it needs and no more. Performed vitamin A in large supplement doses can accumulate to toxic levels over time. Beta-carotene from food does not carry that risk. It is a safe self-adjusting source. A moderate portion of fresh papaya 1 to 2 hours before bed, not a large bowl. The natural sugar in a large serving can create a meaningful blood sugar rise in the evening, which you want to avoid. A cup or so of fresh papaya is the right range. Consistent moderate portions over weeks are far more valuable than occasional large ones. Number 4, pomegranate. Pomegranate is primarily discussed in cardiovascular contexts, but the mechanism that makes it relevant for heart health is the exact same mechanism that makes it protective for retinal blood supply. And understanding this connection changes how useful you find this fruit. The active compounds in pomegranate, particularly pinacolegans and allergic acid, support the body's natural production of nitric oxide. Nitric oxide is a signaling molecule produced by the cells lining blood vessels, and its primary job is to tell surrounding smooth muscle to relax, which widens the vessel and lowers resistance to blood flow. When nitric oxide production is robust, circulation is responsive and efficient. When it declines, vessels become stiffer and less adaptive. What makes this especially relevant for aging adults is that nitric oxide production naturally declines with age. The endothelial cells become less efficient at making it. Vessels gradually lose their flexibility and responsiveness, and the retinal microvascular territory in the body is among the first places where the stiffening shows up as a functional problem. Pomegranate compounds help restore some of that nitric oxide availability. Clinical trials have shown improved vascular responsiveness within 2 to 4 weeks of regular consumption. And a recent area of research is exploring the connection between pomegranate's anti-inflammatory compounds and the reduction of arterial stiffness, specifically in aging adults. Stiffer arteries mean more pressure and more turbulence in the microvascular territories they supply, including the retina. Reducing that stiffness over time directly benefits retinal circulation. Seeds are the cleanest delivery method. A small portion of pomegranate seeds in the evening on their own or mixed with other foods on this list. Unsweetened pomegranate juice in small amounts is also acceptable, but read the label with care because the overwhelming majority of commercially available pomegranate juices contain significant added sugar. If the ingredients list anything beyond pomegranate juice and possibly citric acid, put it back. Number 3, tart cherries. Most people know tart cherries from athletic recovery discussions, but the eye health case for tart cherries rests on 3 distinct mechanisms that work together in a way that makes this fruit more interesting than it first appears. The first mechanism is direct antioxidant activity. Tart cherries contain some of the highest concentrations of anthocyanins of any commonly eaten fruit. Anthocyanins are the deep red pigments responsible for the color, and they have potent free radical neutralizing activity in vascular tissue. In studies measuring markers of oxidative stress in the blood, regular tart cherry consumption has produced consistent measurable reductions for the retina. Lower systemic oxidative stress means less of that burden reaching already stressed retinal tissue. The second mechanism is anti-inflammatory. Chronic low-grade inflammation is one of the underlying drivers of age-related macular degeneration. It contributes to the formation of drusen, which are small deposits that accumulate beneath the retina and are one of the earliest signs of macular disease. Tart cherry compounds have demonstrated meaningful anti-inflammatory effects in human studies, including reductions in inflammatory markers that are directly implicated in retinal aging. Reducing that inflammatory background may slow the progression of early macular changes in ways that other interventions do not directly address. The third mechanism is the one I find most underappreciated: the sleep quality connection. Tart cherries are one of the very few natural food sources of melatonin. Not the large doses found in supplements, but small naturally occurring amounts. 2 randomized controlled trials conducted specifically in adults over 60 found that regular tart cherry juice consumption improved both total sleep time and sleep efficiency compared to placebo. One of those trials found that participants gained an average of 34 additional minutes of sleep per night over the study period. That sounds modest, but in the context of retinal repair, those 34 minutes fall within the deep sleep stages where cellular maintenance is most active. Every additional minute of quality deep sleep is additional time for the retinal pigment epithelium to do its housekeeping work. Tart cherries therefore support the eye through direct antioxidant activity, through reduced inflammation, and by lengthening the overnight repair window itself. That combination is unusually powerful. Small evening portion frozen whole tart cherries, half a cup of unsweetened tart cherry juice or dried tart cherries with no added sugar. The sweetened dried versions sold in most grocery stores are essentially candy. The natural sugar content has usually been doubled or tripled through the drying and sweetening process. Avoid those entirely. Now we enter the final 2 fruits on this list. And I want to mark this moment clearly because these 2 are categorically different from everything that came before. The first 5 fruits support the systems around and behind the eye: circulation, antioxidant recycling, vitamin production, inflammation control, sleep quality. These last 2 deliver compounds that physically deposit into the retinal tissue itself and become structural components of the eye's zone protection system. Number 2, blueberries. The eye health research on blueberries is more specific and more compelling than the general health reputation of blueberries suggests, and most people are not aware of just how targeted this research is. Blueberries are extraordinarily rich in anthocyanins, and the particular anthocyanin profile in blueberries has been studied specifically in the context of retinal function. Multiple human studies have found measurable improvements in visual performance in low light conditions following regular blueberry consumption. These are not vague wellness outcomes. Researchers have measured specific things: Contrast sensitivity in dim light, the speed of visual adjustment when moving from bright to dark environments, and the degree of glare disability when exposed to bright light sources. These outcomes have improved consistently in people consuming blueberries regularly compared to control groups. The primary mechanism involves rhodopsin regeneration in the rod cells. Anthocyanins from blueberries appear to support the speed and efficiency of the rhodopsin regeneration cycle. Faster rhodopsin regeneration means the rods recover more quickly after light exposure and can function more effectively in low light conditions immediately after. This is a direct targeted effect on the specific cells responsible for night vision.